Welcome back to this session. In this session, we are going to give definition of more other types of matrices, and we start by orthogonal matrix. So a square matrix A is called orthogonal if the product of A and its transpose is an identity matrix, i.e., A is orthogonal if and only if A times A transpose is an identity matrix. And so, since if you take a matrix times another matrix, you get an identity matrix, the same definition of inverse of a matrix, then we can say the same thing, that A is orthogonal if and only if A transpose is the same as A inverse. Because if you multiply the inverse of a matrix by the matrix itself, you get an identity matrix. So if the definition of the orthogonal is that the product of A and its transpose is identity, then this transpose of that matrix must be same as the inverse of the same matrix for that equation to always to be guaranteed. And then say if determinant of a matrix A is equals to 1, then A is called proper matrix. If this A is orthogonal and its determinant is 1, then it is proper. E.g., if we have A given by 0, 1, -1, 0, we see that this matrix, its transpose would be 0, 1, -1, 0, and A times A transpose is 0, 1, -1, 0, and then 0, -1, 1, 0. So let's multiply row by column. 0 times 0 is 0 plus 1 times 1 is 1. 0 plus times -1 is 0, and then 1 times 0 is 0. So we get 0 here. -1 times 0 is 0. 0 by 1 is 0, so 0. -1 times -1 is +1, plus 0 times 0 remains to be 1. And this is the identity matrix. And since A times A transpose is identity, then we say that A is orthogonal. That's the definition. And you see that determinant of this matrix A is 0 times 0 minus 1 times minus 1, which is 0 minus minus 1, which is 1. So therefore, A is proper because it's orthogonal and also has determinant 1. And then let's give more examples of orthogonal matrices. If we have another matrix B given by 3 over 5, 0, 4 over 5, 0, 1, 0, minus 4 over 5, 0, 2 over 3 over 5. Let's see whether this is orthogonal. So the first thing we have to get the transpose. So B transpose will be 3 over 5, 0 over 5, 0, 1, 0, minus 4 over 5, 0, 2 over 5. Now B times B transpose will be 3 over 5, 0, 4 over 5, 0, 1, 0, minus 4 over 5, 0, 2 over 5, and then 3 over 5, 0, minus 4 over 5, 0, 1, 0, 4 over 5, 0, 2 over 5. Now, it's usually multiplication of row by column. So 3 over 5 by 3 over 5, we have 9 over 25, plus 0 by 0 is 0, and then 4 over 5 times 4 over 5 is 16 over 5. Over 5 squared, which is 25. So that gives us 1. And then 3 over 5 times 0 is 0. 0 times 1 is 0. 4 over 5 times 0 is 0. So 3 zeros added together, we get 0. 3 over 5 by minus 4 over 5, we get minus 12 over 5. 0 times 0 is 0. And then this will be 3, not 2. It's 3. So 4 over 5 times 3 over 5 gives us 12, 12 over 25, and then plus minus 12 over 25, 0. 0 by this 0, 0, and then 0. 0, 1, 0. So get 1. 0, 0, and then 0. This is minus 12 over 25, 0. This, remember, this is 3. Remember, the reason why we're writing that one, the matrix B was given as this element is 3 over 5, not 2 over 5. So this would be minus 12 over 25 plus 0, and then plus 12 over 25 will give us 0. And then 0, 0, this also 0. Positive 16 over 25 plus 0 plus 9 over 25 is 1. And this is an identity matrix. So B times B transpose is identity matrix. So therefore, B is orthogonal. And then also confirm that this matrix C given by 1 over 3, 1, 2, minus 2, 2, 1, 2, 2, minus 2, minus 1 is orthogonal. Let's quickly prove that. So we have to show that C times H transpose is, so this will have 1 over 3 into 1, 2 minus 2, 2, 1, 2, 2 minus 2 minus 1. So this factor in transpose will mean to be 1 over 3. And then we'll have, so this row becomes first column. So 1, 2, 2. And then 2, 1 minus 2, minus 2, 2 minus 1. Now you multiply 1 over 3 times 1 over 3 is 1 over 9. And then let's do the normal multiplication. So it's row by column. So 1 by 1 is 1, plus 2 by 2. So that's 4. 2 by 2, 4. So 4 plus 4 plus 1 is 9. 1 by 2 is 2, plus 2 times 1 is 4, plus 2 times minus 2, we get 0, because be 4 minus 4. 1 times minus 2 is minus 2. 2 times 2 is 4, plus minus 2 is 2. And then 2 times minus 1, minus 2, and then plus 2 is 0. 2 by 1 is 2, plus 1 by 1 by 2, which is 2, plus minus 2 times 2 minus 4. When you add 2 plus 2 plus minus 4, you get 0. Next, 2 by 2 is 4, plus 1 times 1 is 1, plus minus 2 times minus 2 is positive 4. 4 plus 1 plus 4 is 9. And then 2 by minus 2 is minus 4, plus 1 by 2 is 2, plus minus 2 times minus 1 is positive 2. So minus 4 plus 2 plus 2 is 0. Minus 2 times 1 is minus 2, plus 2 times 2 is 4. And then minus 1 times 2 is minus 2. When you add minus 2 plus 4 plus minus 2, you get 0. And minus 2 times 2 is minus 4. 2 times 1 is 2 times 1 is 2. And then minus 1 times minus 2 is positive 2. So minus 4 plus 2 plus 2 gives you 0. And then lastly, minus 2 times minus 2 is positive 4, plus 2 times 2 is 4, plus minus 1 times minus 1 is positive 1. So 4 plus 4 plus 1 is 9. And it's clear that this, when you multiply this factor 1 over 9 by every element here, we get 1, 0, 0, 0, 1, 0, 0, 0, 1. So clearly, this is the identity matrix, and C times C transpose is what it's giving us. So since C times C transpose is identity matrix, then C is orthogonal. So that's how we prove that. And in a similar way, confirm that this matrix D, so show that D given by a third, we have 2 over 3, we have 2 over 3 minus 2 over root 5, 1 over root 5, 0, minus 2 over 3 times root 5 minus 4 over 3 times root 5 and 5 over 3 times root 5 is orthogonal. I.e., just show that if you take that matrix D and you define its transpose, if you get the product, you get an identity matrix of order 3 by 3 because these are 3 by 3 matrix. Thank you.